like to welcome everybody who's tuning in today. What we're going to be talking about is the pH scale and what it means and what we're supposed to take from that. Some of this I'm taking right from the slideshow that was sent out in your notes. I'm going to be adding a few things to it. We're going to talk about water and how it self-ionizes. We're not going to spend a lot of time at that, but I'm going to spend some time explaining how the pH scale works, talking about how to do calculations involving pH, and also this here, hydronium and hydroxide concentrations. We're going to be talking about what those are and how to use them. So one thing you need to know about water, water does what's called self-ionization. Water molecules, which remember, water just by itself is defined as a neutral substance with a pH of 7. Water, however, can, by interacting with other water molecules, one of those water molecules can act as an acid and one of those can act as a base. Now, if you remember from our definitions of acids and bases, let me see if this will let me draw on here. If you've got a substance that is, let's do red, that is throwing away a proton, so it's sending that proton over to the other one. The throwing acts as the acid, and the ones that does the catching acts as the base. Okay? And so what we have over here on the other side of the equation, this molecule right here has caught that extra hydrogen ion, and so it's now the conjugate acid from that reaction. This one is the one that threw away that extra hydrogen, so it's the conjugate base from that reaction. We refer to this first one right here, this H30, as hydronium. And I'm not going to try and write hydronium with my mouse because I think we'd be here all day. This, of course, OH is hydroxide ion. You'll be familiar with that one because we've seen it a lot before this year. Hydronium concentration is tied to how acidic a substance is. Hydroxide is tied to how basic or how alkaline a substance is. Okay, we're not going to worry about that right there. We're really not going to worry too much about that right there. This slide, though, is pretty important, so I'm going to take just a minute and talk about that. So hydronium concentration, this H30, is tied to acidity. This hydroxide concentration is tied to alkalinity, or how basic it is. If your concentrations of both your H30 and your hydroxide are the same, you have a neutral substance. So if you've got water, you're going to have equal numbers of these and these, because as we saw on the last slide or slide a couple things ago, in order for this to get made and this to get made from water, one of those water molecules is throwing that proton to another one. And so their numbers, their concentrations remain the same. If you've got a substance, though, where you've got a greater concentration of H30, hydronium, then it's an acid, meaning that your concentration of H30 is going to be greater than this number right here, 1 times 10 to the negative 7 molar. On the other side of that, if your hydroxide concentration is greater, if it is greater than 1 times 10 to the negative 7 molar of OH, you have a base. Now, does something about either of these numbers jump out at anybody? If you see it, type it in the chat. I'll give you just a minute. I know they're both the same number, but what is something in there that has to do with pH? Anybody? You see that 7 right there? And that 7 right there? Remember, if something's neutral, it has a pH of 7. Okay, and that little exponent right there is where we get our pH scale from, as you're going to see in the next few slides here. So let me jump ahead. Okay, we're not going to worry about that. Okay, we're not going to worry about that. For that, yeah, let's pause and take a look at this for a minute. Take a look right here. We've got hydronium concentration for a strong acid, okay? And its concentration is 1 times 10 to the negative 1 molar. Okay? This one right here, this 0.1 molar strong acid, this is going to have a pH of 1. Whoops, go back. A pH of 1. This one right here, it's got a 0.01 molar concentration. It's still very strong. Its hydronium concentration is 1 times 10 to the negative 2. This is going to have a pH of 2. So how do I know that? It has to do with this exponent right here. Somebody is drawing on my screen. I don't think that's me. Who's doing that? Maybe that is me. I'm just tripping. Oh, now it's erased. That's weird, dude. There's ghosts in my computer. Get out of here, ghosts. We'll come back to that, though. Let's take a look right here. We've got a 1 times 10 to the 4th molar solution of HNO3, that's nitric acid. We want to know, first of all, what is the hydronium concentration of this solution? Okay, so what we're going to look at here is if the concentration of this is 1 times 10 to the minus 4, if this is a strong acid, and we're going to assume that it is because it doesn't tell us otherwise, we're going to assume that it completely ionizes, meaning that these hydrogens are completely going to split off from these nitrates, which means that every one of those hydrogen ions is going to grab onto a water molecule, and it's going to make a molecule of H30. And so if we've got 1 times 10 to the negative 4 molar solution of this, that means we're going to have a 1 times 10 to the negative 4 molar solution of hydronium. I'm going to swap over real quick to my camera. Y'all see the paper okay? Wow, a little too close. So check this out. We're going to start off, we're going to say this got 1 times 10 to the negative, what was that? 10 to the negative 4. Okay. Is our concentration of H30, of hydronium ions. Okay. Now we want to find what the pH is. And I'm going to go ahead and spoil it for you, or I'm going to let you spoil it for everybody else. Can anybody guess what the pH of this acid is going to be? If you think you know, type it in the chat. Okay. Darius, you're awfully, awfully close. Remember, the pH scale runs from 1, which is very acidic, all the way to 14, which is very basic. Okay, so it's not going to be negative 4, but it is going to be positive 4. And yeah, I hope you're absolutely right. Now, you got that from the fact that it comes out to the negative 4 place. If I was to write this number out, then it's going to look like 0.0001. Okay, it comes out 4 decimal places. That's what that negative 4 is for. Now this right here, if I had something that had a pH, let's say, of 3, then it would have a hydronium concentration of 1 times 10 to the negative third, or 0.001 moles per liter. If I had something that had a pH of 2, we saw this on the slide a minute ago, then it would have a hydronium concentration of 1 times 10 to the negative 2 power, or 0.01. I want you to notice that as the pH scale changes by a factor of 1, the concentration is actually changing by a factor of 10. Meaning that as I go from here to here, this is 10 times more concentrated than this is. This one here is 10 times more concentrated than this one. And if I look at a jump all the way from here down to this one down here, it's 100 times stronger. The pH scale is not a linear scale. It's not like temperature. It's not like, okay, well, it's 65 degrees outside. That's a little chilly, but maybe it'll be 75 later and that'll be a little warm. This is an example of an exponential scale. Meaning that even though it looks like we're just going up by one step, each one step is actually a tenfold increase or decrease from what we had before. Okay, so what if it's like 2 times 10 to the negative 5? Let's talk about that. Because if they give it to you in this nice, easy to follow thing right here, then it's very easy, if it's just 1 raised to a certain power, to figure out what the pH is based on that. If they give you a weird number, though, like the one that Darius just threw at me, is if we've got a H30 concentration of 2 times 10 to the negative 5, well, we can estimate based on this where it's going to be. We can guess that it's going to be awfully close to a pH of 5, but it might be slightly stronger, slightly weaker. I'm going to show you the math here in just a minute, how to know exactly what the pH is, but I don't want to get ahead of myself. We'll come back to this one. I'm glad that you brought that up. Let me jump back over into my slides here. Well, now here's a fun thing. So when we look at any solution, whether it's an acid or a base, its hydronium concentration, hold on just a minute. I want to tell you guys the wrong thing here. Oh, its hydronium concentration times its hydroxide concentration. Let me rewrite that because I can't pencil today. Is always going to equal 1 times 10 to the negative 14. Always, always, always. So if I know, for example, back on my first question that we looked at a minute ago, if I know that my hydronium concentration is 1 times 10 to the minus 4, then I can take this divided by this to get my hydroxide concentration. Now, I don't know if you guys have done much multiplying or dividing using exponents, but the way you do that is you take the base in here and you go ahead and either multiply it or divide it. In this case, we're dividing this by this, which would just give us 1, right? And then if you're dividing, you subtract. If you're multiplying, you add exponents. So negative 14 minus negative 4 is going to give us negative 10. Okay, did I go too fast there? You know what? Don't worry about it if I went too fast. I'm going to show you something I've already given you to help you remember that. But that's going to be true for any solution. If it's a neutral solution, then both this and this are going to have a concentration of 1 times 10 to the negative 7. And so 1 times 10 to the negative 7 multiplied by 1 times 10 to the negative 7 gives you 1 times 10 to the negative 14. Now, I'm going to show you another fun thing here. This right here, because of this exponent, this tells me that I've got a pH of 4. Something that we haven't talked about, and that we're about to, is that there's also a scale called the pOH scale. Nobody hardly ever uses it because it's kind of redundant. It does the same thing that the pH scale does, except that it's flopped. So back on our pH scale, if we have an acid, then it's going to have a pH that is somewhere around the 1 or 2 or 3 or 4 range. If we have a base way down at the other end, then it's going to be something like 14 or 13 or 12. On the pOH scale, though, the pOH scale runs exactly opposite this. So a really strong acid on the pOH scale would have a pOH of 14. I'm sorry, have a pOH of 13. Get rid of that 14 down there. I'm kind of telling lies. If it had a pH of 2, it's going to have a pOH of 12. If it has a pH of 3, it's going to have a pOH of 11. Okay, and if it has a pH of 4, somebody want to beat me to it? What's its pOH going to be? Darius is madly typing. See his forehead leaning up there? It's 10, exactly. Okay, so the pOH back on this guy right here is going to be 10. Here's the other fun thing, okay? Fun thing number 1 is that the concentrations of these two are always going to give you a product of 1 times 10 to the minus 14. The pH of any substance plus its pOH, if you add them together, it's always going to add up to 14. So if you know one, then it's easy to find the other one. You just subtract it from 14 to find the other number. Okay? Now, that still doesn't give us the answer as to how do we get, say, from a weird concentration like this to the pH. And that's going to be the next thing I talk about. Let me see if the slides are going to do us any more good. And if the slides aren't going to do us any more good, then I'm just going to skip the slides. Okay, let's see here. Oh, well, they're telling us what we already know here. Yeah, okay. So there's our hydronium and our hydroxide concentrations. We already knew that. I don't care. Here's the new stuff. Okay. So we're going to be using logarithms. Has anyone in here done anything with logarithms in any of your math classes yet? Or is this all new territory for you? Hope is kind of shaking her head no. All right. So let's talk about what a logarithm is. A logarithm is, it's just kind of a mathematical function that looks at powers of a certain base. What we're going to be using is we're going to be using log base 10. Now the good news is your calculator, if you've got your calculator, already has that built in. Okay. I don't have a TI calculator here with me because mine's an Amarillo in the hot zone, but I'm going to show you real quick, just on my calculator, what that log looks like. Okay. I've got a button that just says log. You've got a button that says log on yours too. If you don't have it in front of you, that's fine. You can look at it later. But the formula, let me put that slide back up. The pH of a solution is equal to the negative logarithm of its hydronium concentration. So let me copy that on my paper right here. Equals negative log H30 concentration. Again, if anybody has any questions, feel free to chime in the chat. I'd love to try and answer them for you. So let's see how that works. Let's say that I've got that, a minute ago we had a hydronium concentration of 1 times 10 to the negative 4, correct? For an acid. Now what I'm going to do is I'm going to take this and I'm going to plug it into this right here. And so I'm going to turn on my calculator. See if I can hold it still enough for y'all to see that. Okay, so I'm going to hit negative log, and I'm going to put in my 1 times 10 to the minus 4. So 1 times 10 to the negative 4. Close my parentheses, and it spits out a 4 at me. I'm sorry that that's hard to see. Okay? And again, that has to do with how many decimal places you've got in this number. The more decimal places out before you get to the 1, that's your concentration. And see now, let's take a look at the one that Darius wanted to see a minute ago. Okay, so pH on this one equals 4. If we've got a hydronium concentration of 2 times 10 to the, he said, negative 5, and we said we thought it was going to be close to 5, okay, just as an estimate. Let's plug that in to pH equals negative log of our H30 concentration, so negative log of 2 times 10 to the negative 5. So I'm going to let my calculator do that for me. So I can put this where there's not too much glare on there. That's not too bad. Okay, so I'm going to hit negative log 1 times, I'm sorry, nope, go back. Negative log of 2 times 10, nope, nerd quit, times 10 to the negative 5. Now we were hoping for a pH, oh, all right, Darius, I'll get right back with you, hold on. So we're hoping for a pH of about 5, let's see. It gives us a pH of 4.698, so we could say that the pH for this equals 4.70, which is awfully close to the 5 that we were estimating it to be. So you were asking, how do I know that the H30 concentration for this one is 1 times 10 to the negative 4? Because let me throw that slide back up here real quick, and I'll have to backpedal some. Okay, we got that from the fact that the solution that we started off with was a 1 times 10 to the negative 4 molar solution of nitric acid. And nitric acid, when you put it in water, every one of these protons is going to split off. So I'm going to have that many protons per liter. Or that, and those protons are going to grab water molecules, and those grabbing those water molecules, let me draw you that instead of trying to just motion it. If I have a hydrogen ion and it's reacting with a water molecule like this, then it's going to make H30. It's going to make hydronium. Okay? Yeah, it'll be something that it gives it to you. I don't know if it's just me, but I'm literally so confused and I'm not getting this at all. Lula dear, please ask a question. We're going to look at a lot more examples though. Okay? Yeah, on a problem like that, it will give you something. Now, I want to direct everyone's attention to something that you already have. I'm going to escape out of this dude right here. And I'm going to refer to this diagram right here. Okay, every one of you should have got that. It's called the big pH diagram. It's in that packet back on Google Classroom. You probably want to get this and either put it as a shortcut on your computer or print a copy out or just handwrite a copy out. This right here is your golden key. It's going to help you for any solution if you know any one of these 4 variables: hydronium concentration, pH, pOH, or hydroxide concentration, then you can follow this diagram right here to find any of the other three. Okay? And once you know how to put this in your calculator, guys, this is so amazingly, amazingly simple. Okay? I'm going to take a look at this pH calculation practice that I gave to you. And we're going to take a look here. Let's start with number 2, because number 2 is one where it gives us the pOH. I'm sorry, where it gives us the hydronium concentration. It says it's 4.26 times 10 to the minus 3. If we were to just go ahead and make a prediction, somebody's writing on my stuff. I don't stop. Freaking me out. Thank you. It's 4.26 times 10 to the minus 3. That's our question. So given that, we want to see if we can find the pH, the pOH, and the hydroxide concentration, and then determine whether it's an acid or a base. Now, in my head, just kind of make a prediction. I'm predicting that the pH is going to be somewhere close to 3. That would mean this is probably an acid, but we're going to come back to that after we have crunched some numbers, and we're going to see how close to that we actually are. Let me go over to my paper here real quick. Okay, 4.26 times 10 to the minus 3. Okay. Hydronium concentration, 4.26 times 10 to the minus 3. You hear my dog in the background barking at literally nothing. That's because she's a genius. And so this is what we're given. Let's go take a look at our big pH diagram. And let's see where we want to go from there. Okay, this is not the right tab. I'm going to go ahead and close that. I want this tab right here. So we know this right here. Now there's a truck driving by. That's probably what the dog was barking at. Hey! Shush! Okay. We're at this point on our diagram. We know our hydrogen because that's what it gives us. Now, we've got two options. We can either go from here and go ahead and find the hydroxide concentration, or down here and we can find our pH. The good news is it doesn't matter what direction we go. So literally the first person who types one in, we're either going to go pH or we're going to go OH. See who gets to it first. Oh, Darius says. I think that's OH. So let's go from H30 to OH concentration. Now, according to this, remember when you multiply these together, the product is going to be 1 times 10 to the minus 14. So all I have to do to find this is do 1 times 10 to the negative 14 divided by my concentration here. So let's do that. So OH concentration is going to be 1 times 10 to the minus 14 divided by 4.26 times 10 to the minus 3. Okay, so I'm going to bust out my calculator. Okay, so I'm going to do 1 times 10 to the minus 14. That should be a 14 and not a 4. Let me fix that. Sorry about that. I'm forgetting my ones a lot lately. It's not a good look for me. I think I'm getting old. That Dane Bramage. Okay, so 1 times 10 to the minus 14 divided by 4.26 times 10 to the negative 3. Okay, so it's going to give me a hydroxide concentration of about 2.35 times 10 to the negative 12. Okay, so that tells me how many hydroxide ions are floating around in there. Now, if you're looking just at these two numbers, and if I was to ask you, okay, which number's bigger, your brain wants it to be this number right here, right? Because you're like, well, 12 is bigger than 3, so that's the bigger number. But this is a negative exponent, which means that this thing right here goes all the way out to 12 decimal places before it starts having any value. This one only has to go out to like 3. So this is a much bigger number than this one here, which again lends credence to our guess that this substance is going to be an acid because the hydronium concentration is a lot higher than the hydroxide. So we have one thing done, and on your paper, you can come in for your OH concentration, and I don't think I'm going to be able to actually write this on there, but let's find out. This ought to be, can mouse this. Okay, 2.35 times 10 to the minus 12, 2.35. Yeah, I thought it would look dumb. 10 to the negative 12. I have so many artist skills there. So we know our hydronium concentration. We know our hydroxide concentration. Let's go back to our big diagram. Now we can either go from hydronium down to pH, or we can go from hydroxide down to pOH. Okay, somebody drew in some arrows. I don't know who that is, but that's awesome that you're doing that. Cool. So somebody besides this time, do we want to go find our P next, or do we want to find our pOH next? pOH says Taylor. Excellent. Okay. So to find our pOH, we're going to start with our hydroxide concentration, and we're going to follow the arrow. The arrow says that pOH is equal to the negative log of our hydroxide. Okay? So let me come back to my paper. So pOH equals negative, come on, pencil. Oh, my pencil's dying. No! Have any more leads? Do I please? You guys have a pencil I can borrow? Don't be ridiculous. Let me get another one. Okay. New pencil, everything's going to be fine. All right, so pH is equal to the negative logarithm of the OH concentration, which means it's going to be equal to the negative logarithm of, we just said our OH concentration is 2.35 times 10 to the minus 12. Sure y'all can see that negative there. So let's get back into our calculator. I'm going to hit negative log 2.35 times 10 to the negative 12. Close my parentheses. Now I am guessing that it's going to be somewhere close to a 12 because the negative exponent is to the 12th power. And if you look here, it gives me an answer of 11.63. So our pOH equals 11.63. Now the only thing that we don't have yet is our pH. Going back to our square diagram, we can get there one of two ways. Now that we have our pOH, we can go straight from here over to our pH, or we can come back to the number we started with and get our pH that way. I'm going to actually do it both ways, because if we do it both ways and we get the same answer, that means that all of our answers are correct so far. Okay, so I'm going to start by going back to my hydronium concentration, and I'm going to say that pH is equal to the negative log of my hydronium. So pH equals negative log of my H30 concentration, which means it's going to equal the negative log of 4.26 times 10 to the minus 3. Calculator, negative log 4.26. Wow, that glare is terrible. Times 10 to the negative 3. pH is 2.37, and we estimated it would be close to 3. So we're going to say 2.37 is our pH. Now, the other way we can check that to make sure it's right, remember back on here that your pH plus your pOH, when you add them up, they're always going to total 14. So let's see if our pH and our pOH total up to 14. Okay, 11.63 plus 2.37. Let's see, 11.63 plus 2.37. I get 14 right on the dot. Sometimes it'll be awfully close, like 13.9 something or 14.01 something. But that tells us right there that we've done it right. So going back to our paper, you could fill those in for your pOH and your pH. Now, based on all the information we have right here, is this substance an acid or a base? What do y'all think? It is an acid. Very good, Riggs. Okay, and the way that easiest for me to think of that is the pH scale, because it's the one we're the most familiar with. If something is between 0 to 7, it's an acid. If something is from 7 to 14, it's a base. Okay? So since this pH is between 0 and 7 and it's closer to 0, this tells me it's a fairly strong acid. And that's how you work pH calculations. I've been talking at y'all for about 40 minutes now. Does anyone have a question? Would you like to look at another example off of that paper? How are you feeling? Another example, please. Okay. Taylor, what number would you like to look at? Let's pull the paper back up here. We just worked number 2. Number 5, she says. Number 5 it is. Okay. So looking at number 5, we have a solution with a pH of 6.02. Now, we can go ahead and answer if it's acidic or basic. If the pH is 6, what does that tell us? It's an acid. Very good. Okay. So you could circle acidic right there. So this time, we're going to be starting with our pH. We're starting down here in this corner of our diagram. So we can go from here. We can either go up to find our hydronium, or we can go over here to find our pOH. I'm going to pick this time, and I'm going to go up to find our hydronium because we haven't done that. We've gone down the chart from concentration to these things. We haven't really talked about how to go backwards, okay? Now, this is a new thing. Let me start a new page here. Looking back at that, starting off with a pH of 6.02. And this we said was number 5. Okay, so pH equals 6.02. So to get from hydronium concentration to pH, you do a negative logarithm. Okay? Well, we need to talk about if you're going the other way, you're going to be doing the opposite of a logarithm. And the opposite of a logarithm, especially a logarithm base 10, is going to set something to do 10 to the negative power of whatever that thing was. So in other words, going off of the diagram, let me pull it up on the diagram so you can see what I'm talking about. If we're coming from pH and going up here to H30, our H30 concentration is going to equal 10 to the negative pH. So H30 equals 10 to the negative pH power. That's going to equal 10 to the negative 6.02. Now, I want to get an actual number there. Is this going to be posted on YouTube? Because I missed the first part. I've been posting my videos on Loom, and I've been putting links in there, and Loom is better than YouTube because the school sometimes blocks YouTube, but it isn't blocking Loom yet that I know of. I'll probably go ahead and put it on YouTube also, but it's your guess. Your guess is as good as mine as to whether or not it's going to show up there. So let me show you how to put this in the calculator. Okay, if you look on your calculator, whether yours looks like mine or whether yours is a TI something, the log button, if you look at the second function of that, I'm going to get in real tight and close here. The second function of that is 10 to the x. So it's the same button, except we're going to be doing the second function. We're going to hit second before we hit that button. So if I want to put this in here, I'm going to put in, I'm going to hit my shift button or my second function button and my 10 to the, and I'm going to put in negative 6.02 because that was my pH. Okay, and it gives me a concentration of 9.55 times 10 to the negative 7. Okay, now you might be wondering, well, wait a minute, King, didn't you say that the pH was supposed to be awfully close to the exponent number? And I did. But if you look at this number is awfully close to 9, okay? And rounding up, this number is actually awfully close to 10. So if I did 10 right here, and I made it a 1, then basically I would move my decimal place one more space there, which would mean I'd only be to the negative 6 power, which is a lot closer to what we'd expect to find right here, okay? Don't sweat the small stuff. I'm just going to put down that my hydronium concentration is 9.55 times 10 to the minus 7, okay? So there's hydronium concentration. Let's go back to our diagram. So we've gone from pH up to here. Let's continue our way where, and that way at the very end we can come back and check and see if these two add up to 14. So I want to go from hydronium to hydroxide. So hydroxide is equal to 1 times 10 to the negative 14 divided by hydronium. Hydroxide equals 1 times 10 to the minus 14 divided by H30. You get out of my garage. Office. Garage, what are you talking about? So it's going to be 1 times 10 to the minus 14 divided by 9.55 times 10 to the minus 7. Y'all see that okay? A bit closer up. So calculator, help me out here. Clear. 1 times 10 to the negative 14 divided by 9.55 times 10 to the negative 7. Okay, I get 1.05 times 10 to the negative 8. For my hydroxide concentration. Now, we're only one step away from getting our last thing. So if we're going to go from our hydroxide concentration down to our OH, we're going to follow this arrow right here. pOH equals the negative log of so pOH equals negative log of my OH concentration, which is going to be negative log of 1.05 times 10 to the minus 8. And so let's get my calculator. I'll hit negative log. I'm going to go ahead and push answer because my calculator knows that that's my answer. And it tells me it's 7.98 for my pOH. Now we can check and see how close to 14 we get if we add this to our original pH. So let's do our original pH 6.02 plus 7.98. Look at that. So we know we did it right. And it is literally that easy on every one of these. All you have to do is identify the variable that they're giving you and then use this square diagram right here to go from wherever it is you start all the way around the square. One way or the other, it does not matter which way you go. I have now been talking for about 10 minutes shy of an hour, so I'm going to go ahead and draw this one to a close unless anyone has any other last minute questions. Tomorrow morning at 10 o'clock, I'm going to have another Zoom conference, and I'm going to at least get you guys started on working through that PhET virtual lab over pH. So I'm going to have it projected where you can watch me working it and you can work right along with me, or you can go back and watch the video just to kind of see how it works. But does anyone have any questions before I say good afternoon? Go ahead and unmute everybody here in case y'all want to, like, shout at each other or something. That's fine. Let's see. Participants, unmute all. Okay. Next, is this paper due? Meaning, am I going to take a grade on this paper? Hope what I might do is what I might do on this, Hope, is I might okay.
Just because you can talk doesn't mean you should do it, Riggs. Oh, roasted.
Then why were you just talking?
See, he's talking about you, not talking about himself. There is a difference.
Yeah.
We don't want to see those. Put those up. What I'll probably do, Hope, is I'll have y'all work on this, and then I might just roll a grade and do a random line. And if you get everything right on a random line, then I'll go ahead and count it as a grade. And if you don't, then I'll roll another one. Oh Lord, who's the big dog?
That's me, Mr. King.
Okay, good to know. All right. Well. All right. Well, in that case, nerds, we'll be talking at you soon. Okay. And yeah, Riggs, I'm going to try and put it up on YouTube and on Loom as soon as I get off here.
So, do we have to download that Loom app, or is it just a website?
It's just a website like YouTube. You just follow. I've got a link on my main teacher page that has a folder with all the chemistry Loom videos, and I'll also link to it in the Google class. So should be easy for y'all to find. Okay?
Thank you.
Okay, sure thing. I will see you guys around. Maybe. Where's my thing? Bye.